This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai Studies. A link is in the description box below. Does the following series converge or diverge? Well, we're going to be using the ratio test in this case because I see a factorial, and factorial means ratio. Now, the rule for the ratio test is based on another limit, so the limit as n approaches infinity, and it's a ratio, so a fraction. So of a of n plus 1 divided by a of n, and we take the absolute value of that, and that's equal to rho. So it's not p, we pronounce this as rho. So ratio and root tests, which we will go over in the next video, have absolute value signs within their tests. And so what that means is that they did the step for us of finding the corresponding positive series. So remember, we're always given a series, and if that series happens to be negative, we could just take the absolute value of that series, if it's negative, and make it positive. And because it's positive, now we can use all the tests that we learned to test for convergence that only work with positive series, like direct comparison tests, limit comparison tests, and integral tests, and so on. But what good is it to test this series if this series is not the same as this one? So how does testing this series tell us anything about the given series? Because the professor is asking if the given series converges or not if the corresponding positive series converges or not. So usually what we've been doing is using our two tools in our toolbox, the definition and the absolute convergence theorem, which together say that if this series right here converges, then that means that this series converges absolutely. And then the absolute convergence theorem says that if the given series converges absolutely, then the series itself converges as well, and then we get an answer. But the difference with ratio tests is that it includes the absolute values already, and so they save us this step of adding the absolute value because they already did that. So by default, we are working with a positive corresponding series. In this case, the absolute value makes no difference because n is equal to 1 and the only things we have are n's, and so we know that it will always be positive. But if it were a negative series, then the absolute value would make a difference because it would make what we're testing related to the corresponding positive series. So by adding the absolute value, the ratio test is saving us a step, and we go straight into dealing with the corresponding positive series. And so therefore the rules are if rho is less than 1, rho is greater than 1, rho is equal to 1. And remember that because of the absolute value with the ratio test, we are dealing with the corresponding positive series. And so the rules here say that if rho is less than 1, then it converges absolutely. But what converges absolutely? We're talking about this given series converges absolutely, but really less than 1 really means that this series converges, right? The series with absolute value converges. And then remember, number 1 tool in our toolbox, the definition, is that if the series with absolute value converges, then we can say that the given series converges absolutely, which is why they just go ahead and skip that step and just say, okay, it converges absolutely, the given series, right? If this is the case, then we can use the absolute convergence theorem that says that if the given series converges absolutely, then that means that the given series converges itself because it converges with absolute value, and it will converge without. So it will converge itself, and therefore we will get our answer. If rho is less than 1, that means that the given series converges absolutely. If p is greater than 1, it diverges, and then if p is equal to 1, it's inconclusive, or if p does not exist. Inconclusive means just use another test. It doesn't mean that there's no answer. So we're just going to take the limit as n approaches infinity of the absolute value of a of n plus 1, meaning we're going to take our a of n, which is this, and we're going to add 1 anytime we see n. So in that case, we have n plus 1 squared over n plus 1 factorial. Make sure you're careful with the factorials. Don't be like n factorial plus 1. No, you're adding the plus 1 to the n, and then we have the factorial. Now, I know it says divide by a of n, but nobody actually says the division part. We actually just skip that step and multiply by the reciprocal of a of n. So we just take a of n and switch. So we multiply by n factorial over n squared. And then here's the step you don't want to forget. It makes things so much apparent. Switch the denominators. So I'm going to go ahead and move this one over here, and I'm going to move this one over here. Because now the stuff that are related to each other are next to each other. Here is a factorial expression that we have to simplify. So which one is bigger, the numerator or the denominator? Well, in both I have an n, but in the denominator I have the n plus 1, so the denominator is bigger. So therefore I'm going to leave the small stuff alone. I'm going to expand the bottom by minus 1 every single time. So I start with what I have, n plus 1, and then to get to the next thing I do minus 1. So that cancels out and we're left with n. And I know to stop here because I have what I have in the numerator, so I can cancel it out, and I'm left with 1 over n plus 1. From here, I can multiply these two together. So that's going to become n squared times n plus 1. If I distribute the n squared, that's n cubed plus n squared. And then the 1 times this is just this. And so we're just left with n cubed plus n squared at the bottom. We can simplify this. So this is n plus 1 times n plus 1. That's n squared plus n plus n plus 1. So that's n squared plus 2n plus 1. So we have n squared plus 2n plus 1. And in the denominator, we still have n cubed plus n squared. And by the way, we don't even need the absolute value anymore because all we have are n's in our problems, and we know that n is equal to 1. Like the least it could be is 1, so it's never going to be negative. So from the get-go, we never even needed the absolute value. I'll leave it in this one, but we don't need it here. Alright, so now we have a really nice rational fraction, and we know what to do when we have those. We just divide every term by the term with the highest power in the denominator, and that's n cubed. So we divide by n cubed, divide by n cubed, divide by n cubed, divide by n cubed, divide by n cubed. This cancels out to be 1. This cancels out to be 1 over n. This cancels out to be 1 over n. This cancels out to be 2 over n squared. And this is just 1 over n cubed. So this becomes the limit as it approaches infinity of 1 over n plus 2 over n squared plus 1 over n cubed over 1 plus 1 over n. And then we can plug in infinity for n. So when we plug in infinity, that just takes the limit away. Infinity squared is still just infinity. Infinity cubed is just infinity. And so anything divided by infinity always goes to 0. And so we're just left with 0 over 1, which is just 0. And so therefore rho is 0, which is less than 1. And so therefore our given series converges absolutely. So I'm going to put that in a sentence. Since, and literally just take your limit, is equal to 0, which is less than 1, the ratio test implies that the given series converges absolutely. But this is not our final answer because the question asked if the following series converged or diverged, not if it converged absolutely, right? And so you use your number 2 tool in your toolbox and say, and absolute convergence implies convergence by the absolute convergence theorem. And so the given series itself converges as well. And that is your actual answer. So no, this is what I used. I used the absolute convergence theorem, the second tool in our toolbox, that says that if a given series converges absolutely, then the series itself converges as well, which is what we have here. The ratio test tells us that the series converges absolutely, so we kind of skip this first step because the ratio test takes care of that. But then if we know that the given series converges absolutely, then we can use our second tool in our toolbox, the absolute convergence theorem, that says that if a series converges absolutely, then the series itself converges as well. And so that's how we get our final answer.